inside of a parallel universe.
Now that we've studied triangles, we're going to move on to four-sided shapes, which are basically quadrilaterals. So a quadrilateral is just any four-sided figure. Quadrilaterals alone don't really have any special properties, so the first one that we're going to look at that's a little bit more interesting is what's called a parallelogram. And all a parallelogram is a quadrilateral with two sets of opposite parallel sides. And this is the definition of parallelogram. But just like with triangles, we didn't write out the word triangle every time. We had a symbol to represent it. So we're going to represent it by a little parallelogram symbol. And all this definition says is that the opposite sides of a parallelogram are parallel. So let's take a look at what that means. So here I have a parallelogram. It could look like our normal parallelogram abbreviation symbol, or I could really reorganize this parallelogram into any configuration. Now, what's true about all of these configurations of a parallelogram is that its opposite sides will always be parallel to each other. Notice that its opposite sides maintain a constant regular distance from each other, making them parallel. Now, how we name parallelograms requires a bit of convention. If I want to refer to a parallelogram, I need to name it by all 4 points that make it up. So I would call this parallelogram A, B, C, D. Now here's one important thing when you're labeling parallelograms. Whatever point you start with, you have to pick a direction that you want to label it in and move around the shape, naming each of the points that make it up. So for example, another way I could have labeled this parallelogram would be, had I gone the opposite way, would have been A, D, C, B. I could also refer to it by starting with point B instead of A and moving around the parallelogram in a particular direction. So I could start with B, and if I move around in this direction, I'd go C, D, A. So I'm basically, as I move around the shape, just naming each point that comes up. An invalid way of labeling a parallelogram would be if you just jump around its points. So say I start with A. If I say A, C, B, D, that is an improper name of this parallelogram because I'm starting with A, jumping across, and then moving up, and then moving down. That's not a valid way for referring to a parallelogram. Let's consider some properties of parallelograms. Here I have parallelogram A, B, D, C. And if you notice, the opposite sides, the orange sides, have the same length. They're both 9.86 centimeters long, and the blue sides, CD and AB, are both 10.7 centimeters long. And if I were to reconfigure this parallelogram, notice that no matter what configuration I put it in, it looks like these opposite sides, though their values change, are always equal to each other. We can say that the opposite sides of a parallelogram are congruent. It's always the case that if we have a parallelogram, the opposite sides seem to be congruent, which we will sum up as opposite sides of parallelogram congruent. Now, let's actually verify that with a proof. So what this theorem actually says is that the opposite sides of a parallelogram are congruent, meaning given a parallelogram, in this case that would be parallelogram AB, CD, we need to prove that the opposite sides, which are AB and CD, are congruent, and the other set, BC and AD, are congruent. So given only that this shape is a parallelogram, it must follow that the sides are congruent. That's the observation that we just made. So like in all proofs, I'm going to start off with my given information. So given parallelogram ABCD, Well, so far, the only thing I know about the parallelograms is how they are defined. So using the definition of parallelogram, I can conclude that the opposite sides are parallel. Therefore, AB is parallel to CD, and BC is parallel to AD. But being parallel doesn't mean that the segments need to be congruent. So to figure out why they must be congruent, I'm going to make a clever construction. And I'm going to draw in diagonal BD, and I'm going to label some angle numbers. Well, because the sides are parallel, particularly since AB is parallel to CD, and parallel lines form congruent alternate interior angles, angle 2 and angle 1 are on alternate sides of transversal BD and on the interior of parallel sides AB and CD, so they'll have to be congruent. Similarly, since BC is parallel to AD, 3 and 4 are alternate interior angles of those parallel lines across transversal BD, so they will have to be congruent at the same time. So I'll state that now. Angle 1 will be congruent to angle 2, and angle 3 will be congruent to angle 4, because lines are parallel if and only if they form alternate interior angles, which are congruent. Then I'm going to point out one other observation, if you haven't noticed it yet, that segment BD is going to be reflexive to itself. Reflexive meaning it's the same as itself. So now I have angle side angle congruent to angle side angle, and triangle ABD will need to be congruent to triangle CDB. So now I've basically converted this four-sided shape into two triangles, which I know how to prove all kinds of interesting things about. So I have shown that triangle ABD is congruent to triangle CDB using the angle side angle postulate. And now that I know those triangles are congruent, I know all their corresponding parts of those congruent triangles will be congruent, namely side AB, which corresponds to side CD, and side BC, which corresponds to AD. So I've proven exactly what I've needed to do So no matter what the shape of a parallelogram, using only the properties of parallelograms, parallel lines, and congruent triangles, I was able to show that this conclusion that the opposite sides must always be congruent. Returning to our diagram for a parallelogram to see if there are any other interesting properties. For this parallelogram, WXYZ, it seems that the opposite angles, W and Y, the red ones, which are both 59.2, and these opposite angles, the green ones, X and Z, are both 120.88. It appears that they also, no matter the configuration of the parallelogram, will also remain congruent. So we'll sum up this idea by saying that the opposite angles of a parallelogram are congruent. And it basically just says that the angles which are across from each other within a parallelogram will always be the same. Now, that was just an observation. To prove it, the proof is actually very, very similar to the proof that the opposite sides were congruent. So let's just change a couple of things. First, I'm going to erase this conclusion. And I want to just point out that the proof that the opposite angles are the same will involve all the same key steps. Only now I'm proving that angle A is congruent to angle C. And rather than proving the opposite sides, we're proving that the opposite angles of a parallelogram are congruent. Okay. And notice that once you prove triangle ABD and CDB congruent, that angle A and angle C are also corresponding parts. So the proof is basically the same. I'm just going to use a different set of corresponding parts of the triangles. Okay. Similarly, you could use the same idea, only rather than constructing diagonal BD, you can construct diagonal AC and prove that angle B is congruent to angle D. Thus, both sets of opposite angles of a parallelogram must be congruent. So now that we've developed all of those ideas, let's see how we can use them in a proof itself. So in this example, given that ABCD is a parallelogram, so we have parallelogram ABCD, and that ED is congruent to BF, I want to prove that angle E is congruent to angle F. Now, whenever you're proving something with a parallelogram, because it has all of these different properties, opposite parallel sides, opposite congruent sides, and opposite congruent angles, it's difficult to label that given information all at once. So my suggestion to you will be to label the most specific information you have, which is in this case, ED is congruent to BF. So I'll highlight those parts, and I'll see what other parts of the parallelogram I might want to use. So again, also my goal is to show that angle E is congruent to angle F. So my suggestion to you would be that if I could somehow prove these triangles congruent, ADE and CBF, then I would be able to conclude that using corresponding parts. Well, in order to get those triangles congruent, I'm going to use the fact that the opposite sides of a parallelogram are congruent, which will give me an extra side in those triangles, and I'm also going to use the fact that the opposite angles of a parallelogram are congruent. And I'll show that angle 1 and angle 4 are supplements of those angles, and then supplements of congruent angles are congruent, give me a side-angle-side relationship. So to quickly write that up, now that we have a plan, first, I'm going to mention that angle 2 must be congruent to angle 3 because the opposite angles of a parallelogram are congruent. I'm also going to mention that AD must be congruent to BC because the opposite sides of a parallelogram are congruent. And then I'm just going to mention that the measure of angle 1 plus the measure of angle 2 equals 180 degrees, and that the measure of angle 3 plus the measure of angle 4 equals 180 degrees by the angle addition postulate. Then that angle 1 is supplementary to angle 2, and that angle 3 is supplementary to angle 4 by definition of supplementary angles. Okay. Then I will mention that angle 1 is congruent to angle 4 because supplements 1 and 4 of congruent angles 2 and 3 are congruent. So supplements of congruent angles are congruent to each other. So now those triangles, which are ADE and CBF, are congruent. ADE is congruent to triangle CBF by the side angle side postulate. And then what I needed to prove, which is that angle E is congruent to angle F, because those are the corresponding parts of congruent triangles, which we just proved congruent.